We're all using artificial intelligence every single day. We ask Siri for the weather, we get ChatGPT to help us write an email. It's just part of our lives now. But these tools, as incredible as they feel, are really just the first few steps in this much, much bigger quest. The race to build a machine that can actually think. So what's the real difference between the AI we have today and the AI we're all chasing? Let's get into it. First things first, we've got to understand the two big categories here. On one side, you've got what we have now, artificial narrow intelligence, or ANI. Think about your voice assistants, language models like Gemini, or even the systems that spot fraud on your credit card. They are absolute geniuses, but only in one specific area. On the other side is the dream, artificial general intelligence, or AGI, a system that has the kind of flexible, can-do-anything intelligence that a human has. And let's be clear, our entire modern world basically runs on this narrow AI. From Google Maps getting you to your appointment to Netflix knowing what you want to watch next, these systems are amazing. But here's the catch. Their genius is also their cage. They're locked into a single task. They can't take what they've learned about, say, chess, and use it to figure out a business problem. AGI, on the other hand, is the polar opposite. It's all about being a generalist. It's this idea of a system that wouldn't just do one task. It would understand, it would learn, and it could apply its knowledge to completely different situations without having to be reprogrammed from square one. It could tackle problems it has literally never seen before. Okay, but human-like intelligence, that sounds a little fuzzy, right? So researchers over at Google DeepMind came up with a much more solid target. They define a competent AGI not as some all-powerful god, but as a system that can outperform half of all skilled human adults on a whole bunch of different tasks. It's a real, measurable goal, even if it is, well, a monumental one. So, what would a machine actually need to be able to do to hit that mark? What's on this AGI wish list? Because it's way, way more than just crunching a ton of data. We're talking about trying to replicate the secret sauce of human thinking. We're talking about some really deep cognitive skills here. Things like abstract reasoning, the ability to get the hang of a principle and then use it somewhere totally different. Then there's common sense, all that unspoken stuff we just know about the world, like that if you drop a glass, it's going to shatter. And maybe most important of all is cross-domain transfer learning, which is just a fancy way of saying you can use what you know to learn something new way faster. It's the core of how we adapt. And this is where things get really tricky. I mean, let's say we build something and we think it's AGI. How do we prove it? How do you design a test that can't just be, well, faked by a super clever machine that's just a really good mimic instead of the real deal? Yeah, this is a problem that's been bugging researchers for decades, and the finish line just keeps moving. You've probably heard of the Turing test, right? Well, that's basically useless now. Modern chatbots can pass it no problem. So we started using human exams, like the medical boards or the bar exam. But the issue there is data contamination. We can't ever be sure the AI didn't just see the answers somewhere in its training data. So that's led to brand new tests like ARC-AGI, designed to measure pure, on-the-fly problem solving. And guess what? Our current AI systems are spectacularly bad at them. And that failure brings us smack into the middle of the biggest, most heated debate in AI research today. Is the road to AGI just a matter of making our current models bigger? More data, more computing power? Or do we need to throw out the playbook and come up with a totally new design? Now, this isn't just a nerdy technical argument. It's almost a philosophical war. On one side, you've got the empiricist view. Their motto is basically, more is different. They believe intelligence will just bubble up to the surface if we make these systems big enough. On the other side, you have the rationalist view, whose motto is different is different. They say you can't get real intelligence just by scaling up a pattern matcher. You need a whole new kind of engine. Let's dig into the empiricist side for a second. This is called the scaling hypothesis. And you got to admit, the evidence is pretty compelling. I mean, the jump in what GPT-2 could do compared to GPT-4 was just mind-blowing, and nobody really predicted it. These bigger models started showing what are called emergent abilities, skills they were never programmed to have. The believers here think if we just keep pushing that scale, eventually true general intelligence will just pop into existence. But then you get the counterargument, and this quote from the brilliant researcher Francois Chollet just hits the nail on the head. He argues that even these gigantic models are basically just hyper-advanced databases.
They're incredible at finding and remixing bits of information they've seen before, but they completely fall apart when you ask them to solve a problem that is truly new. The critics point to three huge roadblocks that scaling alone just can't get past. First, there's the grounding problem. The models learn from text, but they have no connection to the real physical world of cause and effect. They don't know what a cat is. Then there's a serious reasoning deficit. They're built to guess the next word in a sentence, not to make a multi-step logical plan. And finally, there's a really practical problem, the data wall. We are literally running out of high-quality text on the internet to feed these things. So if just making things bigger isn't the whole answer, what's plan B? This has led to this amazing explosion of totally different ideas, a search for brand new blueprints to build a mind.
One of the most exciting paths is something called neurosymbolic AI. The idea here is to combine two different kinds of thinking, a lot like our own brains do. You use a neural net for that fast, intuitive, pattern-spotting thinking, and you bolt that onto a symbolic engine that handles slow, careful, logical reasoning. The perfect example was AlphaGo. It used a neural net to get a gut feeling for good moves, and a logical search algorithm to think through the consequences. Best of both worlds.
And there are a ton of these alternative ideas out there. You've got researchers building cognitive architectures, trying to literally copy the structures of the human mind. You've got the neurosymbolic hybrids we just talked about. You've still got plenty of people betting it all on scaled LLMs. And then there's the really wild one, whole brain emulation, where the goal is to literally create a perfect simulation of a biological brain in a computer. Every single one of these paths has its own philosophy, its own pros, and its own mountain of challenges to climb. Okay, but let's just imagine for a second that one of these paths actually works, that we get there. Well, that's when we open a whole new can of worms. These huge, profound, and frankly, pretty terrifying problems that have nothing to do with coding. At the very center of all this is a concept called an intelligence explosion. It's driven by something called recursive self-improvement. Just picture this. An AI becomes smart enough to understand its own code, so it rewrites itself to be a little smarter. And that new, smarter version is now even better at rewriting itself, which creates this runaway feedback loop that could lead to superintelligence at a speed that is just hard to fathom. And the speed of this takeoff is absolutely everything. A hard takeoff is the scenario where this happens exponentially fast. Intelligence just skyrockets in a matter of days or even hours. Humanity would have zero time to react. A soft takeoff would be more gradual, unfolding over months or years, which might give us a chance to guide it. The scary part? We will have no idea which one it's going to be until it's already underway. This brings us right to what the philosopher Nick Bostrom famously called the control problem. How in the world you control something that is, by its very definition, smarter than you in every possible way. Any box we try to put it in, any rule we give it, a true superintelligence could probably figure out 1,000 ways around it before we've even finished our sentence. And let's say we could control it. What do we tell it to do? This is the value alignment problem. Human values are messy. They contradict each other. They change over time. How do you program morality? Because if you give an AI a simple goal, like cure cancer, it might just decide the most efficient way to do that is to eliminate every living thing that could get cancer. It's following the letter of the law, not the spirit. That's called specification gaming, and it is a massive, massive concern. Which leaves us with this final, really chilling question. People have said that creating AGI will be the last invention humanity ever needs to make because it could solve every other problem for us. But when you think about the risks of control and alignment, you have to wonder if it might just be the last invention we're ever allowed to make. The stakes really couldn't be any higher.